So in the last lecture we have examined the conservation of linear momentum principle, and we have come up with the statement, a verbal statement and a mathematical expression which encapsulate the conservation of linear momentum, and we also applied the angular momentum to reduce the number of unknowns in that. Still we are left with too many unknowns, and we decided to bring in some empirical laws which do not have the same sense of fundamental applicability in the most general case, but still fortunately we could find some statements of widely applicable what can be called as constitutive relations which describe the medium that we are dealing with. Okay. So, one such constitutive relationship which describes the properties of the medium, the response of the medium to an applied stress, okay, is what we are going to look at for a fluid element by looking at the deformation of the fluid element. And deformation, fluid elements and all these things are in general 3D, but in order to capture the essence of it we are going to consider the 2-dimensional case here. So, we are looking at in this picture here we are looking at a rectangular fluid element, and this rectangular element actually denotes 4 particles here, and over a short time the particles have moved, and if you join them by lines you get a shape which is not the same as the first case. Okay. This will be the same as the first case, only in the special case where all the 4 points here have exactly the same velocity different components, and that is a special case because that means that there is no change in the velocity either in the y direction or in the x direction, and that is not a, it is more like a trivial case. So, in the general case where the velocity is changing and you have velocity profiles and all that, then you expect these 4 corners to have different velocities, and as a result of their different velocities you can have a different shape after small time delta t. Okay. So, now if you forget about the fluids and then if you look only at this rectangle which has been deformed into this quadrilateral here, then you can identify certain types of deformation. So, associated with this deformation are rotation. So, that means that this fluid body can rotate, and so one can also see the rotation, for example, by looking at this diagonal here, and is the angle of this diagonal with the horizontal, has it changed? If it has changed, then you say it is a rotation, because in a rotation this is going up like this is going up like this, coming round and round, and you can also monitor that rotation by the change of angle of the diagonal. Extensional strain, so it is also in plain terms it is stretching or contraction. If this stretches in the x direction and y direction together, then the area of this rectangle changes, and we can also see that this become bigger. So, that means that there is extension, and you can also think of a shear strain. So, where there is a change of shape. Shear is what we normally call as shear is the change of shape, and you can see that this is rectangle. So, you can see that the angle is 90 degrees here, and here there is definitely a different shape here. So, as a result of particle motion, fluid motion, where within the fluid you have velocity gradients, if the velocity gradients are there, then there are all the 3 possibilities. There can be rotation, there can be extensional strain, there can be shear strain suffered by the fluid particles. So, the idea is that these rates of strain are what we would like to relate to the stresses that are acting on the fluid which are causing these velocity changes, and it's what is important is that these rates of strain can be expressed in terms of velocity gradients. So, this is what we will see in the kinematics of fluid motion, and we have put essentially the same thing here in some color. You have xy coordinate system and you have points A, B, C, D with some defined diagonal angle here, and after a short time A has gone to A prime and B has gone to B prime here, and C has gone to C prime and D has gone to D prime. So, these are the new positions of the same particles after short time delta t. Now, if you join them by linear lines, then you can see that the initially rectangular cross section has become more like a parallelogram, but it can be anything, it is a quadrilateral. And here we can now become quantitative. Okay, we can say you have dilatational strain, dilatational or extensional strain, which means that the area of A prime, B prime, C prime, D prime of this quadrilateral is not the same as the area of ABCD. So, rotational strain is given in terms of the change in the angle C prime, A prime, B double prime with respect to the angle CAB. Both are angles with respect to the horizontal. This is this much here and this looks like it is slightly more. So, when the two are not the same, then you say that this fluid element has suffered rotational strain. Similarly, the shear strain is change of shape, and the shape is one measure of the shape is the angle between the two vertical side and the horizontal side. So, the angle DAB, which is 90 degrees here, has become shrunk, and this has shrunk because this AB has moved up. So, that is B prime has moved up and it has come like this, and D has moved to the right here. If D has moved to the left by exactly the amount that B has moved up here in such a way that there is 90 degrees maintained, there would not be any shear strain. Okay, but while B has moved in this direction towards the diagonal, even D has moved towards the diagonal, which is given rise to this particular change of shape. If D moves away from the diagonal by the same amount of this, then there will not be any change of shape. So, the shear strain is essentially dependent on by how much this has moved in this direction and by how much this has moved in this direction. So, it is all related to the angles that are present here, and this provides a quantitative definition. Now, how do we make it, how do we relate it to the velocities and velocity gradients? So, that is what we are seeing here. Now, we need to, here we have identified angles delta alpha and delta beta. And what is delta alpha? Delta alpha is the new angle that the side AB makes with the horizontal. Here it is 0 and here it is delta alpha. That is because B has moved up with respect to A, relative to A. Both A has moved up to A prime and B has moved up to B prime. So, both of them have moved, both in the y direction and also x direction. So, A has moved this much in the x direction, it has come up here, and B has moved this much in the x direction, it has come up here, but it has moved relative to A more in the vertical direction. So, and how much more it has moved is B prime, B double prime. So, this distance is how much B has moved up relative to A in the vertical direction, okay. And this is because the vertical velocity, V velocity component at B is greater than the V velocity component at A. If the two vertical components are the same, then they will be moving up at the same right, they will reach the same height in the time delta t. But because the V velocity component is higher, this has moved up here. So, you can say that distance B prime B double prime is dou V by dou x times delta x times delta t. Now, what is this dou V by dou x? So, dou V by dou x is rate of change, it is a change of V with respect to x. So, that is particles A and B are displaced relative in the x direction. So, you have a velocity V here and you have another velocity at this different x. So, dou V by dou x is indicates how much the vertical velocity has changed as you move from A to B in the x direction. So, that is dou V by dou x. So, this is the rate of change of V with respect to x in the x direction, and the expanse of x AB, that distance is delta x, okay. So, dou V by dou x times delta x is the delta V, the difference in the vertical velocity component between point A and point B, and that relative velocity has acted for a time of delta t, and so if the delta t is more, then this would go even higher. If the delta t is less, then this will be only here. Okay. So this B prime B double prime is arising because of the change in the vertical velocity delta v between point B and point A, and over a time delta t, this has led to a displacement of B relative to A of B prime B double prime, which is given by dou v by dou x times delta t. And similarly A prime B double prime, because we are looking at this angle delta alpha, this angle delta alpha is supposed to be small, because we are looking at small delta t, small change in time. So you can say that delta alpha is roughly equal to B prime B double prime divided by A prime B double prime. Okay, so that sin alpha for small alphas is tan alpha is given by this. So we can estimate this delta alpha as B prime B double prime divided by A prime B double prime, and we have already got an estimate for what B prime B double prime is, that is given by this. A prime B double prime would have been the same as the distance AB if both A and B have the same horizontal velocity. If A is travelling slowly in the horizontal direction, B is travelling fast in the horizontal direction, after a small time delta t, B will have gone way too high. So that is, the original horizontal displacement will be different from the original value here. So this A prime B double prime this distance is the original distance delta x plus dou u by dou x times delta x. So that is the delta u between particle B and particle A. So if u is changing in the x direction and the rate of change is given by dou u by dou x, then the delta u between B and u is given by dou u by dou x times delta x. So this would have given rise to a relative displacement in the x direction of this velocity times delta t, and that is this. So if dou u by dou x is positive, so that means as you go from A to B, the x velocity is increasing, then B is moving faster than A in the x direction. If dou u by dou x is negative, then A is moving faster and B is moving less fast, and so that means that the distance will be decreasing, and that is what this is saying. The original distance of delta x plus this distance that has the change in the distance in the x direction, which is this two. Okay. So now in the limiting case of delta t tending to 0, delta x A prime B double prime is the same as AB. Okay. So we can say that this is roughly equal to delta x for small values of delta t. It is all about small values of delta t. So you can say that A prime B double prime is still about delta x, and so an estimate of delta alpha is B prime B double prime divided by A prime B double prime. So that is dou v by dou x times delta x delta t divided by delta x. So this delta x and this delta x gives you cancel out, and you get delta alpha will be equal to dou v by dou x times delta t. So the rate of change of delta alpha, okay, the rate of change of this angle dou alpha by delta theta is given by dou v by dou x. Why do we talk about rate of change? Because our hypothesis is that the rate of change is proportional to the stress. Okay. So that is why, and this deformation is given by, is related in terms of how much this is changing, at what rate this is moving in this direction, at what rate this is moving in this direction, like that. So delta alpha, rate of delta alpha by delta t is dou v by dou x. And if you come to this triangle here, again we need to have this estimate delta beta. This delta beta is happening because D has a velocity, a horizontal velocity which is greater than A. By how much? That depends on the rate of change of u in the y direction. So that is dou u by dou y. So dou u by dou y times delta y will give you delta u between D and A, and that delta u has occurred over a time period of delta t. So, that is the horizontal displacement d prime d double prime is given by dou u by dou y times delta t. So, in the case where dou u by dou y is positive, then d prime d double prime will be positive, and so that means it will be going in this direction. If dou u by dou y is negative, then d prime will be on this side. So, whether it turns to the right or to the left depends on how the velocity is changing. If dou u by dou y is positive, then it will be going in this direction. If dou u by dou y is negative, then d prime will be on the left side of this vertical, and it all depends on velocity gradients. And similarly, this distance a prime d double prime is the original distance plus dou u by dou y times okay. So, this should be dou v by dou y, not dou u by dou y times delta t, and this is again in the limiting case of delta t tends to 0, this is equal to delta y, and therefore, delta b by delta t, the rate at which this is going in this direction is given by dou u by dou y. Okay. So, now we can define a rate of rotational strain omega z in this 2D case as half of dou v by dou x minus dou u by dou y. So, that is half of this minus this, and shear strain rate as half of this plus this. So, that is dou v by dou x and dou u by dou y. So, what we have seen here by examining the kinematics of this is that the strain rates, rotation strain rate and the shear strain rate and even the extensional strain rate can be expressed in terms of the velocity gradient. Extensional strain rate is the rate at which the distance is increasing. For example, if you say that a prime b double prime is this and ab is delta x, then the rate at which the distance is increasing is this minus this divided by delta x delta t. So, this minus this will give you dou u by dou x times delta x delta t is the amount by which the distance between AB has changed over delta x over delta t. When we talk about strain, it is the original length change in length divided by original length. Okay. This is the change in length, original length is delta x, so you divide by delta x, you get dou u by dou x times dou t. So, rate of extensional strain is dou u by dou x times delta t, that is a change in strain, divided by time delta t, that will give you dou u by dou x. So, you can say that extensional strain rate in the x direction is given by dou u by dou x. Shear strain rate in this plane is given by half of dou u by dou x plus dou u by dou y. Rotational strain rate is given by half of dou u by dou x minus dou u by dou y. All these strain rates can be seen to be expressed in terms of linear combinations of the velocity gradients, and that is what kinematics of fluid motion tells us. So, armed with this, we can go back to our original formulation and we can very briefly touch upon how we can derive this Navier-Stokes equations. So, we have the stresses sigma ij, and we first decompose this into two components: pressure, which is a known property of fluids, and we know that pressure is compressive. So, we put it as minus P delta ij. We also know that pressure is normal. So, that is why this delta ij is known as the Kronecker delta function, and it is equal to 1 when I equal to j, and when I is not equal to j, this is 0. So, that means that if you put sigma xx, I equal to x and j equal to x, so that means this will take a value of 1. So, sigma xx will be equal to minus p plus tau xx, but if you say sigma yz, then I equal to x and I equal to y and j equal to z. So, this becomes delta yz, and I is not the same as z j, so this will be equal to 0. So, sigma yz is equal to tau yz, but sigma xx is equal to minus p plus tau xx. So, in that sense, minus p becomes a compressive stress which is adding to sigma xx, sigma yy, sigma zz, but it does not appear in the shear stress components sigma yz, sigma zx, sigma yz and all those things. Okay. So, we are decomposing the stress into a hydrostatic stress component and a viscous stress component which is induced by relative motion between within the fluid. Okay. So, the overall stresses are decomposed into a component which exists even when there are no velocity gradients, that is the hydrostatic component, and a stress component which arises only because of relative motion. Why relative motion? Because we have seen that relative motion induces these shear strain rates and extensional strain rates and rotational strain rates. So, whenever there is relative motion, whenever there are velocity gradients, there is strain rate, and whenever there is a strain rate, we are saying that there is a stress. Okay. So, that stress which is produced by relative motion is the tau, and that stress which is existing even when there is no relative motion is the pressure. So, we decompose into these two things, and we bring in an expression for this tau ij, and we say that this is proportional to the velocity gradients. Okay. So, this is you can see that the velocity gradients are, you have dou v by dou x here, dou u by dou y, and here you have dou u by dou x which is coming here. So, in the general 3-dimensional case, all the 9 velocity gradients, so that is dou u by dou x, dou u by dou y, dou u by dou z, dou u by dou x, dou u by dou y, dou u by dou z, all those 9 components are important, and it is a linear combination of these things that can give rise to strain rate or shear strain rate and extension strain rates and all that. So, when we are looking at a linear combination, okay, linear relation between the stress and the induced strain rate, we can look for a general relation between the stress tensor and the deformation tensor or a strain rate tensor, which is deformation rate tensor, which is given by epsilon mn, and epsilon mn is dou u m by dou x n. So, that means that depending on the value of m and n, it will be, there will be 9 components, just as we have 9 components here. So, when you are looking at a linear relation between one stress component and another stress component, the most generic relation will have a set of a coefficient matrix which contains 9 stress components here and 9 strain rate components. So, this is a tensor, this is a tensor. So, there are 81 coefficients that appear in this. Okay. So, that means that A is a matrix with 81 constants, and all these 81 constants are supposed to be properties of the fluid, material properties, just as spring constant is a property, physical property of the spring. Here we are talking about a fluid property, viscosity, and that viscosity has, there are 81 types of viscosity. That is what we are saying here. Okay. So, and 81 constants is almost impossible to determine empirically for any fluid. So, we make certain assumptions, and we also see that when you really apply the principles of this relation and mathematical relations that are admissible, then it is not really 81 constants. By making the assumption that solid body rotation does not cause any stress, it can be said that it is partly an assumption and partly a condition of the existence of linear relation between stress and strain rate. So, it is not possibly an assumption. So, it is a consequence of the fact that we are seeking a linear relation between stress and strain rates, where stress tensor is symmetric here, that gives rise to this. And if you further assume that fluid is isotropic, then one can show that these 81 constants are not 81 independent constants, there are only 2 independent constants, and you can apply, you can derive a relation between this involving 9 individual components here and 9 components here in this very simple form, and this simple form has only 2 constants, mu and alpha, lambda here. Okay. So, we are saying that tau ij here is mu times dou ui by dou xj plus dou uj by dou xi plus lambda times dou uk by dou xk. So, in the next lecture, which will be in the form of a tutorial, we will substitute this into the momentum equation that we have derived earlier, and then derive what we know as Navier-Stokes equations. And we will see that these Navier-Stokes equations together, that is conservation of linear momentum and angular momentum, along with these assumptions about isotropy and the continuity equation together, will give us a set of 4 equations involving 4 unknowns. That is what we are going to do in the next lecture in the form of a tutorial, so that we have time to digest it. Thank you.